The electric grid is the network through which power is generated, transmitted, and distributed to consumers. The electric grid is broadly made up of three main components: generation, transmission or distribution, and consumption. There are several key pieces of infrastructure that are built to support the delivery of electricity to consumers. It is comprised of these components: generating plants, where electricity is produced; transmission lines, infrastructure that allows electricity to be transported over long distances; substations, where electricity voltage is increased or decreased; transformers, the mechanisms that actually increase or decrease the electricity voltage; distribution lines, infrastructure similar to transmission lines but for lower voltages of electricity. The grid was created to solve the problem of geographic separation between electricity production and consumption. Electricity is often produced far from where it is used, so infrastructure needs to be built to connect the two. Prior to the invention of the modern grid, electricity producers each developed their own distribution systems for delivering electricity to customers. This system was costly and often led to underused infrastructure and wasted electricity. The modern grid was invented to allow various producers to share infrastructure for production and distribution, which led to increased reliability and lower costs. So how exactly does the grid work? After electricity is generated, the voltage is stepped up at a substation. This voltage increase allows electricity to travel long distances while minimizing the amount of electricity lost. The electricity then travels along transmission lines, either overhead or underground. Once it reaches its destination, another substation steps the voltage down to a level suitable for distribution lines that deliver electricity to consumers. The electrical grid provides electricity to various consumers with varying needs. For instance, industrial consumers are large facilities like manufacturing plants. Commercial consumers are office buildings or high-rise towers, and residential consumers are individual homes. The electrical grid is one of the most important inventions in our modern world. The centralized nature of the grid has made it an ideal structure for large-scale electricity production. However, some of the grid's infrastructure is outdated and is not capable of accommodating small-scale electricity generation technologies.
When you flip a light switch, you expect it to work, right? All of your appliances work because your power company has electricity ready to transmit for a lot of customers. And utility companies have gotten really good at anticipating that demand.
If the grid managers are doing their job, you should never notice any of this.
But a rise in solar energy production is making their jobs a bit more complex. Here's a chart that explains why. It's showing demand for electricity at any given time of day. The power companies supply the least amount of power overnight. Then it ramps up in the morning. Everyone's woken up and business gets going. Then at sunset, energy demand peaks. Utility companies will update models like this to operate as efficiently as possible. But the introduction of renewable energy, particularly solar energy, has started causing problems in these demand curves. In 2010, solar panel deployment really started taking off. Most of those installations took place in California, so researchers there started looking into it. They found that the sun produces the most energy at midday, and when you factor in that new midday production, your demand curve changes like this. Every year means new solar capacity, which makes midday demand dip lower and lower. Researchers call this drop in demand the duck curve.
From the grid manager's perspective, the people whose job it is to constantly balance generation and demand, it looks like a drop in demand.
That drop in demand creates two problems. The first has to do with the intense ramps in the new chart. As the sun sets, solar energy production ends, just as the demand for energy typically peaks. Power plants then have to rapidly ramp up production to compensate for that, which is kind of hard to do with the current fleet of power infrastructure. The second problem is economic.
Say you have a couple of nuclear and coal plants. Those plants are only economic when they are running all the time, basically. They run around the clock. And if you have to turn them off at midday, it completely screws up their economics. And plus, lots of utilities just have contracts with those power plants to keep them running all the time. So that creates sort of an artificial floor. If solar generates too much power and there's no use for it, there's no one to consume it, then grid managers just have to turn some solar panels off.
If they didn't, we could risk overloading or even damaging the power grid. So we throw away some of that extra solar energy.
Effectively, what's happening is that solar power is being wasted.
That waste, curtailment, is the big challenge moving forward for solar energy.
If you want solar eventually to power everything or close to everything, you've got to figure out some way of shifting some of it to the nighttime, right? Because the sun's down during the nighttime. The more power can be stored, the more you can sort of let solar rip.
Energy storage eases intermittent power disruptions by storing excess power generated by renewable resources at times of low demand and distributing the power in periods of heightened demand. This helps to balance the load on the energy grid and reduce reliance on non-renewable resources. Combining grid intelligence with renewable resources and an energy storage solution provides a dependable, environmentally friendly, and lower-cost supply of energy.